Hello everyone. In this video, we will understand an important topic in reliability engineering, which is reliability block diagrams explained with practical examples. So what is an RBD? By definition, a reliability block diagram is a graphical representation that captures the reliability relationship between components to determine the overall system reliability. Now this reliability relationship that I'm talking about between components could be a series type, parallel type, a mixed type of reliability relationship, and so on. In simple words, it is a technique used for system reliability prediction. Coming to the application aspect of RBD, are they applicable only to electronics or only to electrical systems? Not really. They can be applied to any engineering system where reliability relationship among its components can be defined. For example, simple mechanical pumping systems, embedded electronic systems, etc. Let us now look at the different types of RBD configurations. There is series configuration, parallel, 2 out of 3, also called as moon configuration, series parallel, that is mixed configuration, or the standby configuration. In this video, we will cover the 3 types shown here. The first one is the series configuration. It means that all components are connected in series within the system. And for this system to function, all the components must function. A single component failure is the system failure. As the name suggests, for the parallel configuration, the components are connected in parallel. Therefore, all components must fail for the system to fail. Even one component functioning will make the system function. The third configuration is the 2 out of 3 configuration, or the majority voting configuration. For 2 out of 3, at least 2 components or subsystems must fail for the system to fail, or at least 2 must function for the system to function. I believe learning becomes real and interesting through examples. So let us understand how to construct RBDs for real world systems with some examples. In this slide, we will see the mechanical pumping system and how to construct its RBD. The function of this system basically is to extract water from the storage tank and supply it to a process. We can see the storage tank here and the process, probably for some cooling or heat exchanger. Now, to extract water from the storage tank, this motor has to work, the pump has to work, the valve has to work, and all the piping and all the coupling between the motor and the pump has to work. Then only the system works. If the motor fails, there's no water. If the pump fails, again there's no water, because each and every component in the system is required to function. Now such a function where all components must function for the system to function is a classic case for a series RBD. So for series RBD, in which all items are connected in series, the general reliability expression is shown here, which is nothing but a multiplication of all the component reliabilities present in that system. Now for this series estimation, the system reliability is always lesser than the minimum of any component reliability which is present in the system. Coming to our mechanical pumping system case, as we saw earlier, there are different components here all connected in series: motor, coupling, pump and valve. Because it is a series system, we multiply straight away all the reliabilities. Assuming a reliability of 0.9 for every component in the RBD, we get a system reliability of 0.6561. Can you see how the system reliability has drastically reduced from the 0.9 value of component reliabilities? This is how the series system actually reduces the overall system reliability. Also, you might wonder how to get the reliability data of these components, motor, coupling, pump, valve. While there could be some standards in which the data is available, however, the best way to get accurate estimates is to obtain the field failure data of these components if they are already in use, or to get it from the manufacturer himself if these are the new components. Now, after the series RBD example, let us now move to example number 2, wherein we are looking at dual redundant power supplies that are commonly used in an industrial type of server. Now, in the figure we can see two power supplies, power supply A and power supply B, both of which are wired in a sharing manner and finally powering the server. In this kind of dual redundant configuration, both supplies must fail for the system to fail. Now, such a configuration is modeled using parallel RBDs, wherein two or more items are connected in the parallel configuration. The general reliability expression is shown here, where R of 1 out of n, which is used for the parallel configuration, is equal to, that is the reliability of 1 out of n architecture is equal to 1 minus its probability of failure, wherein to get the probability of failure of this configuration, probability of failure is nothing but 1 minus reliability, which the term you can see here. So for a parallel configuration to fail, all these n items need to fail. So they are multiplied together, with which we get the failure probability, and this term is subtracted from 1 to get the reliability of this configuration. So for our example, that is dual power supplies, the RBD can be drawn like this, where the two power supplies are connected in the parallel manner and given to the server. And using the reliability expression shown in the previous slide and substituting the reliability values for these power supplies, we are getting a reliability of 0.99. So you can see that the system reliability has improved compared to the individual module reliability, and which is also very intuitive, because now instead of one there are two items to perform the same function. Now such kind of parallel configuration is used when there are critical resources present in the system, such that you do not want a single failure to cause the entire system failure. The third example and the final one we will see in this video is for the aircraft flight control system, which could be in the Airbus A320. You can see in this diagram there are three channels, channel A, channel B and channel C, configured in the TMR configuration, that is triple modular redundancy configuration. In this configuration, at least two components must fail for the system to fail, or at least two components or two channels rather here must function for the system to function. Now these kind of configurations also have voters in them. They are called as majority voters. Who does this? Basically selection of two healthy components in the system. So as I mentioned, these are three identical items connected with the 2 out of 3 majority voter, as shown in this figure here. Now since these channels are identical in nature, we can assume their reliability to be R, and for the 2 out of 3 configuration, the reliability formula is shown here, which is obtained from the binomial theorem, and it's a standard formula for the 2 out of 3 type of configurations. So this is the flight control TMR system. The RBD of the system will look something like this. Now the reliability of this TMR system, after substituting 0.9 for the channel reliability, comes out to be 0.972. Finally, a comparison of the RBDs we discussed so far. In this series RBD, we can also call it 2 out of 2 if there are two components in it. The system reliability comes out to be 0.81, which is nothing but the product of the two component reliabilities. For the parallel configuration or 1 out of 2 configuration, the system reliability is better, that is 0.99. And finally, for the TMR or the 2 out of 3 configuration, the system reliability comes out to be 0.972. Now, if you see their reliabilities, the series configuration has the least reliability. The parallel configuration has the best reliability. However, TMR is also used in some cases because it not only offers high reliability but also other advantages such as reducing spurious outputs with voting. If you want to learn how to decide the configuration of a system based on reliability requirements or how to estimate reliability and availability of an embedded system, I have made a video on it. Hope you like this video. Subscribe to my channel for more videos on this topic. Thanks for watching.